Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this video is about the 737 tail skid. So I'll be looking at the old one position tail skid, the new two position tail skid, effective impact on them, a little bit about aircraft geometry, and then we'll be looking at some examples of tail strikes and discussing the factors that therein to that cause tail strikes. As always, please treat your company training and their manuals as the authoritative source of information. So there are two different types of tail skid on the 737. Not all 737s have got them, but all of the long-bodied series have. So that's the 400, 800, 900, the MAX 8, 9 and 10. They've all got a tail skid. There's the standard the standard one position tail skid shown in the upper photo there. That's on a 400 series from memory, and the bottom photo is showing a two position tail skid in the retractor position. Now, when on stand, they both look very similar. It's actually fairly difficult to tell them apart because almost all the time a two position tail skid aircraft is on the ground, the tail skid is actually retracted. The difference really is that the way to identify them is that on the one position tail skid, the skirt is pretty much straight, whereas you can see on the lower photo the skirt has got a distinct angle about halfway through it, and that's so that when the shoe is presented to the runway, it will be presented to the runway at the optimum angle when the tail skid is extended. Otherwise, you can see from the geometry it may just hit that angle first rather than the shoe, which is what it needs to do. This will become more apparent later when I show you photos of that two position tail skid in the extender position. But if you're on a walk around wondering which one you've got, that's one of the ways to tell. So let's have a look at that one position tail skid in a little more detail. So this is stand on the 400, 800, and the old 900, the MAX 8 and the MAX 8 200. And what it does, it protects the fuselage from tail strike damage during over rotation on takeoff. And that's important to remember, that it only protects the aircraft on takeoff. All tail skids except the 400 have got a drain tube, which you can see just aft of the skirt there on the lower photo. That drain tube has actually got nothing whatsoever to do with the tail skid. It's a drain tube from the APU compartment above it. The aft part of the tail skid fairing is actually part of the APU compartment. You can see the line there going across sort of halfway on the tail skid, just behind the skirt, about an inch or so behind the skirt and the decal. You can see that line across. That's because the tail skid fairing isn't one piece. It separates because the back half is part of the APU compartment. You can see it better on this photo here. So the red dotted line I've drawn on there, that's the outline of the APU compartment, and you can see the three catches on the left hand side there that the engineers would open to hinge open this APU compartment, and you can see that the back half of the tail skid will come away with it. So that's all fairing, all streamlining, if you like, in the back part. That's all it is. And what you've got is, you see on the right hand side of the photo, you've got an air scoop there. So it's like a little tube that comes down and then faces forward into the airflow. So that introduces air into into the APU compartment, and what it does, it purges it of any unwanted vapors or fluids from the from external APU engine leakage and any fluids that might enter through the adductor inlet. Usually rain, to be honest. So it goes around the compartment, and then it expels the air, any liquids out of that drain tube. And the simple reason why the drain tube is long is just to keep the fluids off the aircraft skin. If it was just a hole or a short tube, then it would, it would make a mess all over the back of the fuselage. But it being, several inches long, it's hopefully taken away by the airflow. So that's all that is. No great mystery there. The curiosity is that on the 2-position tail skids, the drain tube is angled to the side, as you can see there. And that is basically just to avoid it being damaged if the tail skid makes contact with the ground. If it's not angled up, it comes down straight, and it will get, the geometry of it will get closer to the runway. Whereas here the tube can be the same length but not go down as far, so it's less likely to make contact with the runway but still be the same length, so still take the liquids away from the body of the aircraft. You can see on the lower photo that after heavy impact it will be worn away. Well, there you go. It's the drain tube it's kind of designed with that in mind. It's I wouldn't quite say it was sacrificial, but it's certainly made from a material that will erode on contact with the runway. So that's the drain tube pretty much covered. Oh no, not quite. There we go. On the Max, it's the same as on the NG, with the exception that the APU shroud, because it's a different shape, because of the different tail section on the Max, it doesn't actually have an air scoop. It doesn't have an inductor hole, if you recall, on the APU. More details of that, go see my APU video. But it doesn't have the air scoop, but the drain tube is the same. Internally, this is I guess where it gets more interesting. This is the internal drawing of the 1-position tail skid. As I say, this just protects the fuselage from tail strike damage during over-rotation on takeoff. Now, so what happens is, in that situation, contact with the runway would, well, it would first wear away the shoe, which you can't see on this diagram because it's underneath at the back, but it's that red block. And then it would, if the contact was a little harder, it would push that tail skid assembly upwards around the pivot points, because it's pivoted at the front there, into the crushable cartridge, which is shown there in purple. The cartridge is attached to a pivot link there, shown in sort of orange, which is in turn attached to the aircraft structure. So that's what it looks like inside, and we can compare and contrast that with the 2-position tail skid. So these photos are showing the 2-position tail skid retracted on the top and extended, as you can see, on the bottom. So it doesn't extend very far. It's actually only 5 inches, but it's considered to be enough. So the 2-position tail skid, as you're probably aware if you saw my previous video on the SFP, that was what it was brought in for the lower approach speeds of the SFP. So it came in 2006, and it's now become it was considered to be so successful. It's now standard on the 900 ER. In fact, it was one of the factors that made the 900 ER, the Max 9 and the Max 10. It's also, as I said, it's an SFP option for the 800 and the Max 8. The main operational difference between the 1-position and 2-position tail skids is that the 2-position tail skid protects the fuselage from tail strike damage both during takeoff and landing. That's the key to it. This will protect the aircraft to an extent for landing, which the old 1-position tail skid never did. So extension criteria, it will extend, say 5 inches or 12.5 centimeters in metric. It extends just before landing. It actually comes down when the gear comes down. So this allows greater angles of attack to be safely flown. That reduces or enables low VREFs to be scheduled, and hence the landing distance reduced. So it's there's no button or switch or anything in the flight deck other than the gear lever. That's what it's what triggers it. So it will extend when the gear is extended in flight, i.e. for landing only. So this does not extend for takeoff. Okay, it only extends for landing. It will retract when the aircraft is on the ground for more than 5 seconds, which is why you never see it extended on stand. Or if the landing gear lever is not down. So as it comes down, when the gear comes down, what they really mean by this is if you've gone around. So for the go around case, the tail skid retracts. Now you may think there's a bit of unnecessary over engineering with having that. My theory for why this happens is because there would be a drag penalty with this, particularly perhaps in the engine out scenario, and that would need to be recertified and what have you, and new graphs drawn up. Whereas I guess Boeing thought, well, if we can make it extend, we can make it retract again. Let's have it retracted for go-arounds. Which, as far as we're concerned in the front, we like that. Anything which gives us better performance, we're all in favour of. The other bizarre scenario when it will retract is if both engines are not running. Now the only scenario I can envisage there is either engine shutdown, but it would have already been retracted after landing, or if you've lost both engines, and again we come back to drag reduction. But then you go, there you are. That's the logic. It extends with the gear, and it will retract also with the gear up, or with both engines not running, or 5 seconds after landing. If you're in the flight deck and you missed it on the walk around, whether you got a 1 or a 2 position tail skid, the idem page will help you out here, and it's shown as a .2 suffix on the model field. That's for the 800 and the Max 8. The .2 suffix is not declared on the 900ER. The Max 9 and the Max 10, because it is standard on those 3 models. So only the optional models, which is the 800 and the Max 8, will it be declared as a .2. The 2-position tail skid, certainly on the NG, it's controlled by the supplemental PSEU, or the SPSEU. Those aircraft got an SPSEU light on the aft overhead panel, which you can see in the upper photo there. On the Max, they don't have an SPSEU. It's like a sort of combined PSEU. Again, for more details, see the PSEU video. But you've only got a maintenance light on the aft overhead. This again, for those that didn't miss that didn't catch the PSEU video, this is where the SPSU is located. It's what's known as the J23 box, so junction box number 23. It's in the E&E bay. You can see it there, circled in the inset photo, and an enlargement of it here with the hatch open, showing space actually for 4 cards, but only 2 are used to my knowledge. One for the mid-exit door control, and one for the 2-position tail skid. So that's where the control for that lives. You will find this switch on the side of the J23 box for all 2-position tail skid aircraft, and this is what engineers can use to extend or retract the tail skid on the ground for servicing or inspections or maintenance, or whatever they might require to do that for. Not something we as flight crew should ever operate, but it's, I guess, as with all my videos, it's good background knowledge to know of its existence. So there you go. If you are tempted to do it, don't forget you'll need hydraulics, and make sure that the area around the tail is clear. It says clear of personnel. I mean, I don't think anyone would be that tall enough, but maybe if you've got a ground servicing vehicle at the back, you know, a honey cart or something, then you wouldn't want to cause it to be damaged there. All right, this video taken by good friend of mine, Captain Tiago Brenner, author of the excellent book Aircraft Performance, Weight and Balance. This shows the movement of the two-position tail skid using that switch. Again, for clarity, the tail skid doesn't normally move when the aircraft is parked. This is being moved by using that maintenance switch that you saw in the previous photo on the J23 box. Remember that it normally extends with landing gear and retracts 5 seconds after touchdown. These drawings are actually taken from the patent, which is a great source of technical information on the aircraft if you want to do your own homework. This was issued in January 2005 during the development of the SFP, and they show the tail skid in the retracted and the extended position. So retracted above, extended below there, and you see that really the basic components, which are pivoting skirt attached to a crushable cartridge and pivot link attached to the aircraft structure, they're all the same as the one position tail skid. The only difference really is that hydraulic ram, the hydraulic actuator there, and the lock links for the extension and retraction mechanism. So it really is very, very similar to the one position. This is a view looking inside the tail skid from above. Now this is the two-position tail skid in the retracted position, and you can see that that in there what you're looking at really are the over center lock links that lock the tail skid in either the extended or the retracted position, and they work. These over center lock links are really the same as it works in the landing gear. Again, cast your minds back to the landing gear video for an explanation of those. The SPSU tail skid card controls a relay, so there's an electrical signal sent to power a solenoid-operated hydraulic system A control valve in that tail skid actuator. So it's electrically controlled, hydraulically operated. The actuator acts on the forward lock link, breaking the over center lock, causing that the cartridge and tail skid to extend or retract is how that works. So let's look at the effects of impacts on the tail skid, how it works. So I've already kind of mentioned this the shoe. Now this really is what's used, or should be the only part used during a gentle impact with the runway. So gentle contact, it will only wear the shoe down by friction with the runway. The actual skirt fairing won't move with gentle impact. It'll stay in the same position. So if you've had one of those and you go back and look at the tail skid after you got on stand, you may see that the warning placard is still green and indeed unchanged from where you picked up the aircraft that morning. The only way you will be able to tell that you had a light tail strike, if I can call it that, is by looking at the condition of the shoe. And it's for that reason that many operators paint the shoe red, so that any wear will show up more easily, because remember that shoe is made of metal. So once you scuff that along the runway, you will expose the bare metal, which will show a colour contrast against the red. So that's what you should be looking for then. Just because you've made contact with the runway doesn't actually mean that the shoe will need replacing. You've got wear dimples there that you can see on the lower photo, and surprisingly, you can go again with the shoe scuffed, as long as it hasn't been scuffed or worn down to the wear dimples. And there are two on the back, which you can see in this photo, and another pair on the front. When it reaches the wear dimples, it must be replaced. In my experience, the engineers will usually replace it as soon as it's had any kind of touch with the runway. But you know, legally you can continue with it until you reach the dimples. Now, if whilst the shoe is in contact with the runway, it hits an object, and by that we would hope we're talking about centerline lights or something. It may cause it to that impact may cause the shoe to break off. Again, there's no big drama or crisis with that, because it's actually designed with that in mind. There is a shear channel there, and the shoe can shear off without causing any secondary damage to the rest of the tail skid. So that's gentle impact. It should all be confined to the shoe. Hard impact, on the other hand, the impact will actually occur at the shoe, but it will start to push the whole skirt up into the tail skid fairing. Remember, this skirt is hinged at the front, so the back end, which is where the shoe is, will push up into the fairing. Now inside you've got a cartridge, which you can see in that bottom photograph there, with a before and after. A new cartridge is on the left, clearly, and a post tail strike cartridge is on the right. These are a lot of thought has gone into the design of these to make them able to absorb the force of a tail skid without damaging the aircraft. So they've got to try and take the right amount of force and still push back, you know, on the aircraft against the runway, to prevent any further damage being done. So this is made of aluminium, which, as we know, is a relatively soft metal. I mean, if it was made of too hard a metal, it wouldn't crush. If it was made of, I don't know, cardboard, it will put up no resistance at all. So it's made of aluminium, or aluminium honeycomb. And it's also got a hollow center core, and again that hollow core is there to give the crushed aluminium honeycomb somewhere to go, so it doesn't all displace it out to the side. It goes into the middle as well, and builds in a little bit of resistance in there. So I say that the purpose of that is to try and absorb the force of the tail strike without damaging the aircraft. Now, if this happens, the skirt fairing will push up, and you will it will register, if you like. You'll see this from the outside, by where the warning placard is against the fairing. So it'll probably be up into the red, depending on, you know, how good a job you did with your tail strike. Again, surprisingly, if you push the skirt fairing up and you're still in the green, the cartridge can go again. It won't need replacing. It only needs replacing once you get into the red. Again, my experience talking to engineers, and I'm not an engineer, but talking to the guys over the years, if there's been any damage to these, they tend to replace them. So you've got the full impact protection for next time. Now, in recent years, a warning appeared in the FCOMs, which was that cartridge assembly warning placard must be checked as soon as possible after the tail strike. The tail strike skirt fairing may re-extend due to gravity as time passes, resulting in a reading error on the warning placard decal. Now, they must have put this in because it happened, and probably happened more than once. I didn't think it could happen, but there you are. We're all here to learn. Obviously, the danger there is that you have a tail strike, you don't know you've had a tail strike. Time passes, you go out and do a walk around, or probably if it's your last flight of the day, maybe the aircraft can go several hours either before an overnight inspection by engineers or by the next crew, and this thing could re-extend due to gravity. So with that in mind, it's probably not bad practice to just check your tail skid as you leave an aircraft. Even if only to prove that it wasn't you that did the next tail strike that aircraft had. I just put it out there for you. It's worth considering. Only takes a minute to do, and could prove useful. Okay, that was hard impact. If it's really bad and you have a very hard impact, then what will happen here is that the impact of this will actually force the whole cartridge up so rapidly. It may or may not crush, or it may go beyond where it goes for crush, but there is a fuse pin designed into that pivot link. Fuse pins, as we know, are designed to shear at a certain threshold, and what will happen is that the skirt and cartridge assembly will then push up as one into the fuselage without pulling on that pivot link, which could have done secondary damage to the aircraft structure. So that's your third level of protection, if you like. So light impacts, it's all taken up by the shoe. Hard impacts, it should be absorbed by the cartridge, and with very hard impacts, you'll break the fuse pin, and then we're into serious structural inspections after that. As was undoubtedly the case here. Now, these photos are actually from an accident report to a 737-800 registration there. I've put that on not to name and shame the aircraft or operator, but just so you can Google this and find the report yourselves. If you just put that into a search engine, you will find the report and this and several of the photos beyond. But it's quite useful. I know a lot of engineers watch these videos as well. We got station numbers listed there, and it certainly for the aircrew, it shows in the inset diagram at the top where your damage is likely to occur. And it's a long way forward of the tail skid. In such extreme cases as events like these, the tail skid won't absorb all the damage. In fact, on some, as I'll come on to tell you when I talk about the geometry of it, the tail skid might not actually even be touched because the impact happens so far forward. But with events like these, clearly, as you can see, the skin of the aircraft can be punctured, or certainly worn so thin that it needs to be reskinned. You can actually also damage frames and stringers, and sometimes even the aft pressure bulkhead. And again, saying this to aircrew, the aft pressure bulkhead, that should ring bells with you as to why the QRH drill is structured the way it is. Again, I will come on to that later. Oh, here we are. So the QRH procedure. It makes no distinction between a soft or a very hard tail strike. If you if you suspect or have confirmed that you've had any form of tail strike whatsoever, then this is the procedure that you must follow. So it assumes the worst case scenario, which is that pressurized flight with significant damage to the skin can lead to a structural failure, and it therefore directs you to manually depressurize the aircraft and land as soon as possible. So pressurization mode selected to manual, and get the outflow valve out to full open so that the aircraft can't pressurize, and land at nearest suitable airport. Obviously, you'd hope that you detected this quite soon after takeoff, but you know that. Again, I'll show you an example in a moment where a crew were not aware that they had a tail strike, and it's not that uncommon. In which case it may be the airport which have observed it. Then time's passed while they've sent out an inspection vehicle to inspect the runway, and then called on to you, by which time you could be 10, 15, 20,000 feet and already starting to pressurize. So so you may need to do this to actually depressurize rather than stop pressurizing. All right, on to the geometry of it. Again, we've already alluded to this, but let's spell it out. So we'll talk first about the one position tail skid case first. So the drawing at the top is the takeoff case. And for takeoff, the closest point of contact with the runway is the tail skid. The lower drawing is the landing case, and the closest point of contact is actually the fuselage, not the tail skid. And the difference is that for landing, the main gear struts are compressed. That's the key difference here. You don't get that on takeoff. The struts are extended, from when you walk around, when the aircraft's boarding, taxiing out. You take off, the struts extend. On landing, they compress. And depending upon the body angle and the amount of strut compression, because there are several variables in here, your contact point could well be the fuselage. Now, the two-position tail skid aims to address that. So for takeoff, there's actually no change. The two-position tail skid, it remains retracted. No additional protection was deemed necessary by Boeing for the SFPs. So for takeoff, the contact will continue to occur at the tail skid. But for landing, the tail skid, as we know, it extends 5 inches, and that changes the point of contact from the fuselage to the extended tail skid. Again, this this depends upon the body angle and the amount of strut compression. But that's the difference. I think those diagrams help make it clear that what we're doing is we're changing that point of contact from being the fuselage to the tail skid for the landing case. All right, so looking at the graphs here, this graph is from the flight crew training manual, and you'll find them all in there. This particular one I've chosen is for the 737-800, and you'll see that the area that I've highlighted in red there is the ground contact pitch angle with the aft fuselage. So we're not bothered about the other side, nose gear, nacelle, flap track fairing. We're just talking about the aft fuselage and the tail skid. And you will see that there is a difference of ½ a degree there between the one position tail skid and the two position tail skid variants. And in actual fact, the two position tail skid, you could look at that and say, well, this is making it worse because my contact pitch angle is reduced by ½ a degree. Well, yes, it is, but the increased protection that you get from it enables the lower approach speeds to be flown. And we're talking about, just to put some numbers on this, and again, this is just throwing back a little bit to the SFP presentation. The VREF is reduced by around about 7 to 8 knots at flap 30 and 4 knots at flap 40 compared to the similar weight approach with a one-position tail skid aircraft. So it does give significant advantages in performance. You just have to be a little bit more careful about tail contact. So looking further at landing geometry, this table, which I've compiled for all 737 models except the 100, which would be even better than the 200. This shows the ground contact angle, i.e. the tail strike attitude, for a normal landing for various models of 737. And as you can see, the longer body length gives a reduced tail strike attitude. No great surprise there. And as we've already seen from the previous slide, which showed the FCTM graph, a two-position tail skid reduced the ground contact angle by 0.4 of a degree. So takeaways from this, really the high-risk aircraft, as though you didn't already know it, are the on that list alone is the Max 9, and well, I don't know. I'm tempted to say the Max 10 as well, but obviously we don't know what they've done with the landing gear yet, how that's changed this. I haven't yet seen the data for the 10, but I will be watching with interest. But nevertheless, I'd say that really the at-risk aircraft are certainly all the 900 models. The 800 not so much. I mean, you've still got to be careful. But the 900s and the 9s, they're the ones to be careful of. Okay, exceptions to geometry. Not a title Pythagoras would have approved of, I'm sure. But so what we've got here is a photograph of a 737-800, and I've included the registration there again, not to name and shame, but so that you can Google it and look for the accident report yourselves to read in your own time. But the gist of this is that following an unstable approach, and Boeing say that unstable approaches are the prime cause of landing tail strikes by a long way. The last data I saw, which admittedly quite old, was that I think 3/4 of all tail strikes stemmed from unstable approaches. Anyway, this was an unstable approach. It touched down with engine thrust higher than idle and without flare, resulting in the aircraft bouncing up 4 feet. Thrust was reduced to idle during the bounce, causing the spoilers to extend, resulting in a sudden loss of lift. The second touchdown was just over 3G. A go-around was initiated, reached a pitch attitude of 8.6 degrees, which interestingly was less than the 9.2 required for a tail strike according to Boeing. And it was believed that the gear compression from the high impact landing caused the tail strike at a lower angle than expected. And if I can just flick back one moment to this table, what I've actually written and the way this data is presented from the FCTM is that these are the ground contact angles for a normal landing, and that means for normal shock compression, oleo compression. So on here we've got a 3 and a bit G touchdown, which is considered not a normal landing. So the compression of the shocks was more. So the contact pitch attitude was less than you would expect. Your approach speed, your touchdown speed will have an effect on the tail skid, on the contact angle. Again, this graph from the FCTM, it shows the variation of touchdown body attitude with delta V from VREF. If you're not familiar with this graph, then do take some time to have a look at it, particularly if you're flying the long-bodied aircraft. takes a little bit of getting your head around, but you've got VREF down at the bottom, and then as you go up, so typical contact pitch attitude around about 6 degrees at VREF. The solid lines are flap 30, the dotted lines are flap 40. And this is for an SFP 800, so 2-position tail skid 800. So at VREF, you're safe. You're a good three or so degrees away from contact. At VREF -5, you're getting close, and at VREF -10, you are likely to have a tail strike. So as I've written on the side there, allowing the speed to drop anywhere below VREF, particularly with flap 30, makes tail skid contact possible as the struts compress. So watch your speed on touchdown. Next variable, this is for the takeoff case, obviously, so it's the effective takeoff flap. Again, I've compiled this from all the FCTMs from the originals right up to the max. And this is all I've included here is for takeoffs of flaps 1 and 5. The tables you have in the FCTM go right the way up to 25, but it was obviously clearly going to be way too busy to show it on this one slide. And really, the at-risk area is flap 1 and 5, which is why I've shown those. So 1 and 5 is where you've got less tail clearance than the higher flap settings, because lift-off attitudes are higher. And the FCTM actually says, consider using a larger flap setting for takeoffs at light gross weights. In other words, where you can. They also say that aft fuselage contact is unlikely in the 200, 500, 600, and 700. If you look at those numbers, you could probably add a couple more to that list as well. But again, you can see that on the 8 and 900, which are the most common models, you've got a tail strike attitude there of 11 degrees on the 800 and 10 degrees on the 900 and the max 9. So could be worth going for higher flap settings just to improve your tail clearance, because you're down to 13 inches of tail clearance on the long bodies at flap 1, and 13 inches isn't a lot. So this video taken, I think it was earlier this year, late last year. It shows a BBJ-3 or a 900 ER taking off from a wet runway at Glasgow. The aircraft unsticks normally, but then pitches up further, making contact with the tail skid after the aircraft has got airborne. And thanks to Daniel Sander for use of that video. Okay, so let's have a look at some more tail strike case studies and the factors surrounding them. This photo here is from a 737-800 tail strike at Birmingham in 2018, following a takeoff contact, and it shows the extent that the damage is confined to the tail skid drain tube and probably the cartridge. So there was no fuselage contact as you would expect on a takeoff case, because the oleos are not compressed. But there's a significant amount of damage there to the tail skid. That looks like it's been, probably full cartridge compression on that one. Possibly even the shear pin gone as well. But interestingly, in that event, given the amount of damage, you may find this surprising, but the crew were not aware of the tail strike until air traffic asked them. Because the incident was spotted by a member of ground ops, I think, at the airport. They called it through to air traffic, and air traffic called the crew and said, you know, are you aware? And they said no. Anyway, the crew in flight then rechecked the takeoff performance data to see if there was anything amiss, and asked the cabin crew if they'd heard anything on takeoff. They replied that they heard a strange noise but couldn't identify it. So again, you know, as with all good CRM tips, you know, use the resources available to you, and the cabin crew sat at the back, they'll probably be the first to know whether you've had a tail strike or not, although they may not know what it was. Anyway, again, that accident report's available to read from the AIB website. My takeaway point is that if you have a tail strike, you may not know you've had a tail strike, even a fairly hard one. This event was due to an erroneous, a mistrim stabilizer, which was as a result of erroneous weight or CFG data. So this happened because of a loading error, and what happened in this case was that as the crew set takeoff thrust at the start of the takeoff roll, the aircraft just tipped up on its tail, and this apparently happened at about 5 knots according to the report. It was literally seconds after toga was pressed, and before the M1s had even got up to takeoff thrust. The aircraft just sat back on its tail and did that damage there. Okay, now this clip is of a 737-900ER, and you can see that it bounces on the first landing and then has a tail strike on the second touchdown before going around. And this is actually a fairly common tail strike scenario. Now, I want to state that my intention in showing this is not to criticize the crew at all. I don't know what went on in that flight deck. I wasn't there. I don't have the data. I'm not saying anything against the crew. All I want to do here is just pass on some technical observations to people, which may help an understanding of the technical aspects surrounding such events. So, points of interest that caught my eye when I watched this video. First of all, it was a 900ER. So we've already seen from the tables that are put together there that the ground contact angle of 10 degrees or even less with landing gear compression. It's the lowest of all the 737 models. So really, this may not have happened on another model of 737, but on this one, you know, if it's ever going to happen, this is where it was happening. Second, it bounced to a bulk landing, and at no point did the fuselage appear to make contact. And the photo I've got here is just a little screen grab from the moment of tail strike. And I've played this through frame by frame several times, and I couldn't see fuselage contact. So the two-position tail skid here really did its job in just giving that little safety buffer, which prevented damage to the fuselage. My third point is that the speed brakes didn't deploy until the second touchdown, and you can see in this photo, you can just see a little bit of speed brake peeking up above the leading edge of the wing there. So this is at the second point, and at takeoff the spoilers are still deployed. So let's go through those points. First question is, why didn't the speed brakes deploy on the first touchdown? Because I'm sure if they had, the bounce may not have occurred. I mean, I don't know, but it would have been less likely to occur. So if we go to the FCON and just run through the criteria for speed brake deployment, what you need is for all of the following to occur. Speed brake to be armed, on NG the rad alt to be less than 10 feet, the landing gear strut compressed, and just to specify, the right main landing gear brings the ground spoilers, any main landing gear brings the flight spoilers. Both thrust levers to be at idle, and the main landing gear wheel spin up, in other words, to be above 60 knots. Now, again, I'm not privy to any information other than this video, but it would appear to me that the most likely scenario here was that the thrust lever were not at idle, because all of the others were probably all the other criteria were probably met. The only possible one that may not have been met might have been the landing gear strut, but I doubt it, because on the NG we've got sensors on each wheel. We've got 2 sensors on each wheel, unlike the classics where it was only on the right. So the most likely scenario is that the thrust lever was not at idle, and now why that happened I don't know. I'm not going to speculate, but the FCTM gives the following on bounce landing recovery. It says that if higher than idle thrust is maintained through initial touchdown, the automatic speed brake deployment may be disabled even when the speed brakes are armed. This can result in a bounce landing, which is what we've seen or appear to have seen in this video. Now, during the resultant bounce, if the thrust levers are then retarded to idle, automatic speed brake deployment can occur. This results in a loss of lift, nose up pitching moment, which can result in a tail strike or hard landing on the subsequent touchdown, which is what we appeared to get. The point of this is that what this is saying is that during the resultant bounce, if the thrust levers are then retarded to idle, automatic speed brake deployment can occur. It kind of implies it can occur in flight, yet you need the landing gear strut compressed. So I must admit, for me, it's a little bit of a grey area. I don't know if once the gear is compressed, it sends a signal and says, right, we're on the ground. If that's cancelled during the bounce, but the wording implies to me that the speed brakes can deploy on the skip, if you like, during the bounce. Now, question is, why did the speed brakes not subsequently retract? Because I've stepped through this video frame by frame, and as the aircraft took off for the second time, if you like, so you know, for the bulk landing, the speed brakes are still extended. Now it's a little difficult to tell exactly when they are, but the FCOM tells us that the speed brakes will automatically retract when either thrust lever is advanced. Now, it wouldn't have got airborne if the thrust levers hadn't been advanced, so they absolutely were. The FCOM says after an RTO or landing, if either thrust lever is advanced, the speed brake lever automatically moves to the down detent and all the spoiler panels retract. Spoiler panels may also be retracted manually by moving the speed brake lever to the down detent. Well, it probably happened automatically. Now, as I say, the angle of the video hides the exact moment where the speed brakes are retracted, which is a little bit of a shame. But in all probability, as I say, having looked at this many times, the speed brakes were being commanded down by the thrust lever position. They must have been, because obviously takeoff thrust was applied to go around. But I think that the point here is that the response is fast, but not immediate. It can't be immediate. There's a mechanical process to go through. So it's probable that they had retracted by the time that the aircraft was airborne, but by then the tail strike had already occurred. So that's my take on that. Looking again at another event, this one's on a 737-800 with a single position tail skid. This follows a bulk landing, so a very similar situation to the one we just saw the video of. It shows how far from the fuselage the fuselage contact can occur if the tail strikes on landing. Again, this is the single position tail skid aircraft. in addition to the fuselage damage, that you can see the tail skid's been pushed up beyond the decal. That suggests that the tail skid shear pin has been broken. If you can't even read the decal, then you know it's been quite a significant tail strike. Okay, and the last case I'll look at is holding off the runway in the flare. Now, we've got a video here of again a 737-900ER, so you know the most vulnerable of the 737 models. It appears to land in a normal attitude, but then it rotates upwards. It sort of pitches up after touchdown with possible fuselage contact. Now, that rotation could be aircrew input. Again, I don't know. I wasn't there. I'm absolutely not here to judge. I'm just here to add some technical insight if possible. But the other reason could very well be that the deployment of the speed brakes will cause the aircraft to pitch up as the lift is destroyed behind the CFG, and this is actually a design feature of the aircraft. I mean, it's a legal requirement of the design of the speed brakes that they must not cause a pitch down when they're deployed, which would exacerbate an overspeed condition. So the aircraft will pitch up, and the previous extract that we read from the FCOM also echoes that. So if the risk is that if you delay lowering the nose onto the runway, as the speed brakes deploy, it will pitch you up on, you know, give you an uncommanded pitch up, if you like, which could cause tail contact. Now, Boeing lists the following factors as factors which can increase the chance of a tail strike in this situation. First, allowing the airspeed to decrease below VREF prior to the landing flare, resulting in a high pitch attitude, and we saw that in the graphs in the flight crew training manual earlier on. Second would be trimming the stabilizer nose up just prior to or during the landing flare. And again, I hope we all agree that during the landing that you should not be trimming the aircraft. It's a transient maneuver. All the inputs should be done with the control column on the elevators. Holding the aircraft off with increasing pitch attitude and attempt to make an extremely smooth touchdown. Well, I'm sure in the early days we've all been guilty of doing this. What can I say? It's not good technique, and if you're in one of these long-bodied 737s, you're running the risk that this crew here almost had the tail strike. Fourth, touching down with an increasing pitch attitude. Again, go for the touchdown attitude and hold it. And finally, failure to fly nose gear onto the runway immediately after main gear touchdown, which, as discussed, because you could leave yourself open to the pitch up effect of the speed brake deployment. So there it is. That's the tail skid, and a little bit of insight, I hope, on tail strikes. As always, if you've enjoyed this video, please give it a like, subscribe to my channel if you haven't already done so, and if you want to read more, consider getting a copy of the book. Thanks very much for listening.